Go. Okay. Does that look okay, Pablo?
Yes.
Okay, good. Well, it's a pleasure to speak here. It's been a while since I gave a colloquium, and I really want to do it in person, but and we're almost there, actually teaching in person, but colloquia are still not quite there yet. So I decided to do it by Zoom. So I'm going to talk today about isotope separation, Maxwell's demon, and the Pointsman Foundation. So the first topic is isotopes. And I don't mean by that the AAA baseball team from Albuquerque, New Mexico, but rather isotopes of the elements. These were discovered by Frederick Soddy, who won the Nobel Prize in Chemistry in 1921 for this work. It means literally equal place because it means that they occupy the same place in the periodic table of elements. And we now know that they differ from one another only by the number of neutrons in the nucleus. As an example, isotopes of lithium, there are two stable ones, lithium-6 and lithium-7. Lithium-6 is about 7.5% natural abundance, lithium-7 is the rest. And I'll say more about lithium in a moment. I'm sure you've all heard of alchemy and the old belief that one could convert base metals into precious metals like lead into gold. It was a long-standing dream. Even Sir Isaac Newton thought it was possible, but alas, we don't think it's possible today. But on the other hand, what we can do is something that is in some sense better, and we call it, or at least I've called it, nuclear alchemy, because we can literally transmute one element into another by means that have been developed over the past century. What makes isotopes interesting? There are many stable isotopes. There's about over 250 stable isotopes of the elements throughout the periodic table. But one can expand that list considerably using methods that have been developed since around the 40s. The two primary ones are shown here, cyclotron, which accelerates protons, and a reactor, which has neutrons, and both of them can transmute elements, create radioactive elements of various half-lives, and those can be separated using radiochemistry. Interestingly, in Austin, we don't have any cyclotron. Our closest medical cyclotron is in San Antonio. And so for one of the key isotopes that is used for imaging, it's less than a 2-hour half-life. And so you have to get on a fast, hope that you don't have a traffic jam. Hopefully soon we will have a cyclotron in Austin to actually make isotopes here at hospitals. But what we do have actually is a local reactor. Not all of you know that, but we have a 1 megawatt reactor at the Pickle Research Center. And we actually intend to use it there with the director, Bill Charlton. And typically you have a target material and you irradiate it and you create a radioactive isotope, which can be separated by radiochemistry, but only if the target material and the radioisotope are different elements. Otherwise, chemistry does not work. And I'll say more about that in a moment. That's actually pretty restrictive because in many cases, you'd like to have the target and the radioisotope be the same element where chemistry cannot work. What I learned, and I have to say, I didn't know this before I got into this whole field, and I'll describe how I got into it, but I didn't quite realize how important isotopes are, and in a way, have not realized their full potential by a long shot. They are already finding applications in cancer therapy, malnutrition, as tracers, medical imaging, basic science, and new materials. And I could give a talk on each of these topics. The first question you might wonder is, how do you separate isotopes? Certainly, we know how to separate elements using chemistry, but isotopes of an element have almost the same physical and chemical properties. And so, except for the lightest of the isotopes, generally chemical separation is not possible. And so you have to turn to other methods. And I'll review briefly three of the main methods that are used today. The first one you have heard about probably is the gas centrifuge. The second one is the calutron, and the third is laser separation. So let me start with the centrifuge. This was actually invented by Jesse Beams at the University of Virginia in 1934, where he demonstrated that one could separate isotopes of chlorine gas using a centrifuge. And today, this is a very refined, very advanced technology that is shown here in a picture that I lifted from Urenco stable isotopes, which produces isotopes by centrifuge separation. But one of the key things to know about this is that it only works for atoms or molecules that are in gas phase at room temperature. And that includes, of course, noble gases, halides like chlorine or bromine, and most notably uranium separation due to the fact that you can make a stable molecule, uranium hexafluoride, which is gas phase at room temperature. But I would say that gas centrifuge is not a general method because it requires this gas phase condition. So it really only works for a very small set of elements or in the periodic table, and most notably uranium. The next method is known as the calutron, which was invented by Ernest Lawrence. He won the Nobel Prize in Physics in 1939 for the cyclotron. The calutron was a variation which used, I'll show in a moment how it works. He named it this way because cal was for California, U was for uranium, which was what it was used for initially, and tron is tron. I don't know what that is. Cyclotron, calutron. How does a calutron work? Well, it's a device that separates by charge to mass ratio. So the starting point is you take an oven and you heat up an element and form a vapor in vacuum. So you make an atomic beam. You ionize the atoms by electron bombardment. And then you accelerate the ions in a potential, and you create a large magnetic field on the order of a few Tesla over a very large volume. And in that magnetic field, cross-electric magnetic field, the ions undergo a curved trajectory where the lighter ions have a smaller radius of curvature, and then you can collect them in pockets, and that gives you the separation factor. This is an old technology, was invented in the 30s, and initially was used for uranium separation, but after World War II, that was abandoned in favor of the gas centrifuge. So today, the modern, and I put modern in italics, is a Cold War era, circa 1950 machine. And you can see that from this diagram, which actually shows diffusion pumps, so you can get a sense of how old this is. These are very large and very expensive machines, but they haven't changed. I mean, the technology really has not changed in over 80 years. But what I will say about the calutron is that it's a very general method. It can work on almost any element in the periodic table. So that's its advantage. The third method is laser separation. And this was a long-standing dream that you could use tunable lasers to selectively ionize an atom by using the frequency shift, which is known as the isotope shift, which slightly shifts the resonances of one isotope relative to another. The method, which is called atomic vapor laser isotope separation, or AVLIS for short, relies on multi-photon ionization, and the pretty picture here. But unfortunately, it's a very difficult method in the sense that it requires very, very high intensity lasers, primarily due to the fact that you have to excite an atom to the continuum, which is a non-resonant process. So after years of effort, the program was terminated. The US spent a lot of money on doing this and finally abandoned it. And so the common wisdom was that laser separation does not work, but we're going to revisit that. Now, to give you a sense that isotopes are not easy to separate, let me take a simple example, and that's an element which you are all familiar with, calcium. Calcium Shown here is a alkaline earth. It looks like a bright metal, silvery metal under vacuum, and it sells for a few dollars per kilogram. Now, if this sample that I show here happened to be calcium-48, calcium-48 is a rare but stable isotope of calcium, so about 0.2%. One out of every 500 calcium atoms is calcium-48. If you could get a kilogram of that, this is how much it would cost, $130 million. Now, in full disclosure, I used the same picture for both calcium and calcium-48 because I couldn't find a picture of a kilogram of calcium-48, but it would look identical. Physically, it would look identical. And this is not explained by the natural abundance, because if a factor of 500 would have said that this should have cost on the order of $10,000, not $130 million. That gives you some idea that isotope separation is not an easy task. And in fact, there's a worldwide supply crisis of enriched isotopes. And the US closed down its large Calutron program in the late 90s, leaving the only large Calutron facility in operation in the world is in Russia. And I don't need to tell you that today that is in serious trouble. It was even before, but now it's even really a crisis. And so there's an urgent need for new methods due to the importance of the isotopes, as I'll explain. Now, so I gave you an overview of the existing methods, and it's clear that we need something new. But before I go into that, I need to pivot a little bit and tell you something that goes back well before we even knew about isotopes. And that is a thought experiment proposed by the great scientist James Clerk Maxwell. In 1871, his thought experiment is known as Maxwell's demon. Although he didn't coin that, that was coined by his friend Lord Kelvin. And apparently Maxwell hated the term because it sounded very spooky. And in fact, the picture that is drawn, this is a cartoon that I lifted from Wikipedia, looks very spooky indeed. It shows a creature known as the demon who could see the coming and going of every gas phase molecule or atom and could open a trap door, thereby, if letting atoms go through, for example, if he sees something coming from side B, he could open the door and let it go through side A, but otherwise keep it closed. And in such a way, the demon would cause all the particles to move to side A of this two chambers, thereby lowering the entropy of the gas. Maxwell was, although he proposed this idea, he actually said it was impossible to us. And I would say that aside from some demonstration experiments on single particles, this still remains impossible to us, at least the way it's shown in this cartoon. Because in the cartoon, the spirit of Maxwell's demon is not a single particle, but actually a very large ensemble, perhaps Avogadro's number of particles. Can one actually do this? And that remained a thought experiment for about 140 years. Now, independently, some time ago, it was around 2004, so that's already almost 18 years, we came up with an idea, and it was a construction. It was a simple construction, but we asked a different kind of question, and that is, can we make a one-way wall for atoms? That would be a device that would let atoms go through in one direction, but not back. And we came up with some ways to do that. And generally, they rely on having a combination of a conservative potential, which could be a magnetic field, plus you need something to break the directionality. And that is broken by an irreversible process, which for us is optical pumping. I'll explain that in a moment. But it involves cycles of absorption of a laser followed by spontaneous emission. And we showed not only how you could construct this, but also that you could then use this to cool atoms in the same sense of lowering their entropy as Maxwell had envisioned. What we also rely on, it turns out, although at first I don't think we completely understood this, but now it is completely clear that what is happening actually is due to not the momentum of the photon, but rather its entropy. And maybe I'll explain that in a moment, but that's a kind of a new paradigm that you could use photon entropy to do something useful. Well, a one-dimensional toy model is nice, but in the end, real life is in 3 dimensions. And so my group set out to do the experiment. And 3 years later, we reported this result and then followed up with other experiments where we proved that we can indeed use this method to cool atoms. We increased so-called phase-space density by over a factor of 300. So it was a significant effect. And I think it's pretty clear that this was the first experimental realization of Maxwell's demon, at least for ensembles of particles, in a way that Maxwell himself thought about. How do I know Maxwell thought this way? Well, I learned about this courtesy of Bruce Hunt, who is in the audience, who told me about this letter that Maxwell wrote to Lord Rayleigh in 1870. And just to quote a little bit, he said, "I do not see why even intelligence might not be dispensed with and the thing made self-acting, allowing all particles going in one direction while stopping all those going the other way." So essentially what Maxwell realized is that the way this could work is not by this creature that would see everything in advance, which seems impossible even today, but by an automatic one-way wall that just works. And now he didn't know how to construct it. We needed atomic physics and we needed lasers, but that was the idea. And so I think Maxwell would agree that what we are doing is exactly his thought experiment. Now, this actually has some useful applications, even in cold atom physics, and this is something that we're continuing to work on. One of the first applications we hope to do in collaboration with other groups is to use this as at least a partial alternative to evaporative cooling of atoms. There's a process of cooling where you throw away the hot atoms, and it works, but it's very lossy. And this was the basis for proposing to the Keck Foundation that we could construct an ultra bright atom laser, and it was funded by them, and we made a lot of progress, but we're still not there, where we could get Bose-Einstein condensate with much, much larger numbers than previously possible. What would that be useful for? Well, some basic physics experiments, for example, a proposal by Roger Penrose to test quantum mechanics plus general relativity by creating superposition states of separated Bose condensates, but the number has to be big enough for the effect to be visible. And also we're interested in proposals for gravitational wave detection in a mid-band part of the spectrum with separated atomic interferometers, which was proposed by Dimopoulos et al. And there are other proposals for gravitational wave detection, but they rely on having much larger number of atoms. So I think cooling atoms is interesting and important, and we hope to continue some of that work, but that's not the main focus of my talk today. So the talk today is something different, and it relates to isotope separation. And so what I want to tell you is that this same concept of photon entropy and this one-way wall can be used not only for cooling purposes, but also for sorting, of the same type of sorting that we would need for isotope separation. And indeed, by using the photon entropy of a laser, so we can achieve separation with very, very high efficiency, as I'll explain. We call this method magnetically activated and guided isotope separation, or MAGIS for short, and claim and have proven now that this is a replacement for the calutron. So it relies on two important ingredients, and they are not new. In fact, optical pumping was proposed and demonstrated by Alfred Kastler, who won the Nobel Prize in Physics in 1966 for this. This idea and demonstration is now a workhorse of atomic physics. And it basically says that if you have a source of atoms shown in the upper part of the picture, creating an atomic beam, and you can tune a laser to an atomic transition where by choosing the right polarization of the light, you can place the atom into a desired magnetic state. And this happens by selection rules that preferentially will populate one of the magnetic states by cycles of absorption and re-emission. So in the picture shown here, the ground state has 3 magnetic states, the upper state also has 3, and by using right circularly polarized light, you can walk it over after several events of absorption and spontaneous emission. So at the end of the cycle, you're concentrated all in the plus 1 state. And by changing the polarization, you could alternatively put it into the -1 state or the 0 state. Now, the way an atom responds to an external magnetic field is very different depending on the state. So in the +1 state, it is repelled by the magnetic field. In the -1 state, it's attracted. And in the 0 state, it's unaffected. So just by tuning that polarization and light, we can polarize or magnetize the atom appropriately. And by using the isotope shift, we can choose which one we do this to. The other ingredient is just a way to make large magnetic fields. With, of course, we could use superconducting magnets, but we choose to use a simpler technology. These are basically just refrigerator magnets, powerful ones, rare earth magnets. And by arranging these permanent magnets in a particular configuration, known as a Hallbach array, where we rotate each bar magnet by 90 degrees relative to its neighbor, what you find is that the magnetic field on one side is maximized at the expense of the other side. So we can create very large surface fields over a Tesla, very close to the magnet, but optimize that. And we put this together in this following picture, cartoon, which kind of illustrates how MAGIS works. So again, the upper part shows an atomic beam where we evaporate element of interest, and let's say we have two isotopes, one, or in this case, three. One is shown with the desired one is the solid line, and we have a laser beam which optically pumps that particular isotope to a magnetic state that is repelled by the field. The other ones are in the m=0, like the upper trajectory, where it just doesn't see the magnetic field and crashes into this array. And the third one and below is where it's attracted, so it's pulled into the field. Now, on the right-hand side, we have collectors. But if you look at this geometry, there's no line of sight from the left side to the right side. So an atom traveling in vacuum, which will travel in a straight line, cannot reach the source of the atoms to the collector, only if we magnetize it. And so by tuning the laser to the right transition and choosing the right polarization, we can pick out that isotope and reject all the other isotopes. So this is a simple picture. It relies, in fact, you can understand in terms of entropy, it really is that the laser beam has a source of zero entropy photons. But when an atom takes it and absorbs it, that photon, it spits it out in all directions, thereby increasing the entropy of the photon. In this case, we're not cooling the atoms, we're demixing them. But demixing is also an entropy reducing activity. So the advantages of this approach are, first of all, optical pumping is very efficient. With a few photons per atom, we can polarize or magnetize these atoms with nearly 100% efficiency. We can separate these atoms by a magnetic field acting on the magnetic moment. So while the calutron separated by the charge to mass ratio, and charge is always the same, but the masses are different by maybe 1% or so for the heavy elements. In our case, we're separating by magnetic moment to mass. So forget the mass differences. We can change the magnetic moment. We can even change its sign. And so we have a huge lever arm as opposed to the calutron, where we can do this separation on very short meters type scale, where we can achieve very large separation factors. Also, because we use surface magnetic fields with permanent magnets, there's no current, so we're not using any energy for this process. But finally, and I'll say a little bit more later, the possibility of hot separation, because of the small footprint of our method, in principle, we can use this pre-irradiation to separate stable isotopes of the elements, but we can also use this post-irradiation, for example, in cases where the target material and the radioisotope are the same element and radiochemistry is not possible. In that case, MAGIS can still work. And this opens up great possibilities that were not available until now. In fact, it really, you could say it's an alternative and a replacement for radiochemistry in certain cases where especially where radiochemistry is not even an option. It's because I love history of science, and so it's always interesting for me to understand better the motivations. I was fascinated by the fact that Maxwell was really inspired when he thought about Maxwell's demon. He was inspired by the historic pointsman of the railways. This was the person that switched the tracks. So you had this train carrying goods, and the pointsman flipped a lever and caused the train to go one way and another. And Maxwell found this very interesting because it was an expression of free will, as opposed to the Newtonian point of view, where if you know the particle's position, momentum, and the equations of motion, you can predict where it's going to be sometime later. Whereas in the case of a pointsman, you can alter the future by human intervention. And Maxwell, in fact, that was motivated by this, as far as I understand, to think of his demon. In the case of that we are doing it, we can think about this as an atomic pointsman, as a variation of Maxwell's demon applied to this situation of switching a switchyard of tracks. But so let me take this picture and shrink it down. This is my poor man's version of the movie. Since I'm not very good at the PowerPoint, I made my own little movie. And the smallest font is called Atomic, by the way. So that's the very smallest font there, which you can't even see. But that's the shrunken atomic pointsman. And we proposed initially, to do this to demonstrate this on highly depleted lithium. This is pure lithium-7 without any lithium-6 component, which is needed for nuclear reactor cooling water. Because if you have lithium-6 in the cooling water, lithium-6, when it's bombarded with neutrons, converts into tritium, and the tritium will exchange with the hydrogen, so you get tritiated water, which is a radioactive hazard. And so there are strict rules about removing all the lithium-6 from lithium-7, and lithium-7 is used as a buffer in the water. So there's a great need for this, and guess where it's made? Russia and China. So there's real almost strategic issues with depending on highly depleted lithium. So we proposed this idea in a paper back in around 2012, I believe, and we predicted that using the MAGIS setup, we could achieve an isotopic purity in a single pass of 99.95%. That, by the way, is the industry standard. That is what is required. And scalability to kilograms per year at the efficiency of a few photons per atom. Well, what do you do when you have an idea and your proposal? You write a proposal. You write a proposal, to, in this case, to DOE, but it was rejected. And I won't show you the referee reports, but this cartoon illustrates it. I don't know if you can read the caption, but it says, your proposal is innovative. Unfortunately, we won't be able to use it because we've never tried something like this before. So this is what you typically encounter when you're proposing something new. And so I was pretty desperate because I knew this was going to work. And so at the time, I went to my dean, it was Marianne Rankin, the dean of the College of Natural Sciences, and I explained to her what this was about and why I thought this was important, and she provided the support with no questions asked, and it enabled us to do the work. And in fact, a few years later, the experiment worked even better than I imagined. We exceeded the predicted purity of 99.95%, and the scalability and efficiency were as predicted. This was published and patented. And at that point, typically in academia, you do this work and then you say, okay, let me move on to another topic. But in this case, because of the importance of the isotopes, and I already recognized that these could be very important, especially for medicine, I felt that there was a need to take it from the laboratory and make it happen in real life. And of course, one option would have been to make a company, but I really had no taste for that, at least not initially. And so instead decided to make a nonprofit foundation, which for historical reasons called it the Pointsman Foundation. And you can understand now why. So this is a nonprofit research organization. It's called a 501c3, tax exempt, which at least initially, this was our mission statement. We'll use the efficiency of MAGIS technology to greatly reduce costs of separated isotopes, make life-saving therapies and diagnostics more readily available to the global medical community. This is our starting point, but actually the vision is much bigger now. But this is where we started, and you can read a little bit. This is now quite outdated, but in 2016, there was a little write-up in Physics Today. We have a new president and CEO, and I'm very excited to announce that Marianne Rankin agreed to become president and CEO of the Pointsman Foundation. She has been involved from day one and really a great supporter and believer, and she will help us help lead this effort to do all the things that we want to do. Marianne, of course, is known to many of you as former Dean of the College of Natural Sciences. She was CEO of National Math and Science Initiative, and then Senior Vice President Provost at University of Maryland. We have a board of directors. I serve as chairman of the board and founder, mostly medical doctors, MDs, real doctors, as we like to say. Stephen Abrams, you can see by his white coat, he's a medical doctor. He's a pediatrician at Dell Pediatric Research Institute. Steve is a pioneer in using stable isotopes of iron and other minerals to assess malnutrition and through using them as tracers, and I'll say more about that in a moment. Potentially very impactful work. Mark Epstein is a professor of surgery and very concerned about problems with post-op infections and infectious disease, which plague surgery and implants. Peter Fox is a radiologist, director of the Research Imaging Institute at San Antonio, at the Medical School of San Antonio. Joe Jurczyk is an oncologist, director of hematological malignancies sections at Columbia University Medical School. And Doug Stone is another physicist, friend, theorist, and supporter. We have an advisory board consisting of Stephen Chu, former Secretary of Energy and Nobel laureate in physics, Ted Hensch, Nobel laureate in physics 2005, our own Ray Orbach from UT, who was also former Undersecretary of Science at DOE, Neil Lane, former US Science Advisor and former Director of the National Science Foundation. Our newest member, I'm very happy to say, is David Reitze, well known to many of you, Executive Director of LIGO, and also UT alumnus awardee. Daniel Zeifman is a professor at the Weizmann Institute and former president of the Weizmann Institute of Science, and very supportive of our goals. So let me say a little bit about what isotopes are being used for at the Pointsman Foundation and beyond. The first thing that we are tackling is cancer therapy, and there is great promise of targeted radioisotope therapy. And the way this works is by having a targeting molecule, which may be a monoclonal antibody or a peptide or some other, or nanobody or something, aptamer, something that is designed to seek and attach to tumors in the body, even if they are metastatic. So even if they spread throughout the body, these targeting molecules can find and attach to them. But you, by themselves, they won't do anything, but you arm them with a warhead, and that is the radioactive isotope, which could be a beta emitter, electron, or an alpha emitter, or possibly a gamma emitter, or in some cases, it will have all three. And together, this has been shown to be very, very effective in treating cancer, especially metastatic cancer. It's been held back by the availability and cost of the isotopes, but we're entering a golden age of designer molecules. So this specificity of the targeting molecules is getting extremely high. And really, by reducing renal toxicity, one can do almost therapy without the bad side effects that one gets from chemotherapy, for example. Of all the radioisotopes, there are many candidates, but the one that has really emerged in recent years as a maybe perhaps the most promising radioisotope of all for therapy is lutetium-177. Lutetium is in the periodic table as a lanthanide, so-called rare earth, on the lower right side of the periodic table. It has a half-life of about 1 week. It's a beta-emitting isotope, about half an MeV, which translates into about 1 millimeter range in tissue. It has a small branching ratio of gamma emission, which can be used for imaging purposes. And it has just seen an explosion of activity and many, many clinical trials, and approved already for cancer therapies, different types of therapies throughout the world. The way one produces lutetium-177 is there are two pathways, basically. One of them is using stable ytterbium-176. So ytterbium is also a lanthanide, one space over to the left of lutetium, and the 176 is a stable isotope, about 12% natural abundance, and you irradiate it with neutrons, and you create ytterbium-177 that lives for about 2 hours and decays to lutetium-177. This is called the indirect route, and because ytterbium and lutetium are different elements, the lutetium can be separated from the ytterbium target by radiochemistry. But as I said, all the supply of ytterbium-176 to date is from Russia, and the whole industry is in danger of collapse if that is disrupted. So the other pathway is called the direct route, and where you start with stable lutetium-176, which is about 2% abundant, and you irradiate with neutrons. Notice the cross section is over 2,000 barns, and for those nuclear aficionados, that's a huge number. That means that it's very, very efficient in production. In any reactor, you can really make copious quantities. But there are some downsides. One of them is that you can't separate the lutetium-177 from the target material by radiochemistry because they're the same element. Secondly, you make a long-lived impurity, which is a metastable state, lutetium-177M, which has a half-life of about 160 days, and that's a real problem. So, so far, the direct route has not been done, is at least not used for therapeutic purposes, but there's great potential there, which we will take advantage of. And when we analyzed this, we found that MAGIS is ideally suited to ytterbium-176. First of all, we know everything about ytterbium. In fact, ytterbium has even been trapped and cooled and even Bose-Einstein condensed. So virtually everything is known about it. Some of the best atomic clocks are based on ytterbium, actually at NIST and Boulder, neutral ytterbium atoms. For our purposes, ytterbium has zero magnetic moment in its ground state, which means that in the MAGIS setup, if we do nothing to all the isotopes, they simply don't get through. And that's a good thing. It's relatively low temperature, it's a non-toxic element, and we have lasers that we can optically pump it and magnetize it in a metastable state. And we've already demonstrated that at the Pointsman lab, we've demonstrated purity that is beyond the industry standard, beyond what the calutron can do. And we're going to do even better than that. So, and things are moving rapidly now. And I'll just quote two press releases. The first press release, and so this is all public information. That's why this talk can be recorded, is because I'm telling you things that are out in the public. There's a press release by Eckert and Ziegler, which is a very well-known radiopharmaceutical, radioisotope company, international company. Their headquarters are in Berlin. They signed a joint venture and exclusive long-term supply for ytterbium-176 with Atom Mines LLC, an innovative, I'm just reading the press release, innovative producer of enriched ytterbium isotopes, and a subsidiary of the nonprofit Pointsman Foundation, both based in Austin, Texas. So interesting point, and this is what I always thought for several years. My hope was that we could incubate our work at the Pointsman Foundation using philanthropy and institutional support. And then when we're ready, we would then be able to commercialize it, but retain ownership, majority ownership. And that's exactly what we've been able to do. So Pointsman Foundation is the majority owner of Atom Mines LLC. And we're going to replicate that with other isotopes in the future. So this is a really kind of a unique situation that we will have a for-profit, nonprofit that will bring in a lot of revenue for the Pointsman Foundation. The second press release is very recent, just a few weeks ago, by Novartis, the pharmaceutical giant that has invested already over $6 billion in cancer-fighting drugs that rely on lutetium-177, and FDA gave it full approval for treating metastatic prostate cancer on March 23rd, so a few weeks ago. And this is a big deal. Novartis is very committed now to lutetium. There are many other companies with pipeline drugs, all based on lutetium-177. So in the time that remains, I want to say a few words about our future projects. And I really could give a talk about each of these, cancer therapy, medical imaging, and so on. These are topics that kind of the short list for the Pointsman Foundation, and some of them don't even involve isotopes. For example, clean water and air, early cancer detection are ideas, some of them patented, some still under development. Some of them have no connection with isotopes, but the common theme is using the physical sciences, advances in physical science and engineering to benefit humanity. But I'll just say, because I have limited time, I'll just say a few words about prevention of iron deficiency and something to end about fundamental physics, because that's where I start and that's where I go back. Those are my roots. So let me tell you a little bit about iron deficiency. And perhaps you didn't know this, I didn't know this some years ago, but amazingly, sadly, 2 billion people, at least worldwide, suffer from iron deficiency. 50% of children in the world, mostly in developing countries, but even in the US, about 15% of all children in the US suffer from iron deficiency. And when it gets more severe, it's called iron anemia. It causes severe developmental problems, permanent brain damage in growing toddlers, especially from the ages of 1 to 4, and it's not repairable. So this impacts their whole lives. This can be solved. There is no need to have iron deficiency by iron fortification of foods and beverages. But if you don't do it correctly, nothing good comes of it. And in fact, there's lots of examples where iron supplements were given and they didn't have any outcome because they just literally passed through the body without being absorbed. This was known a long time ago, and again, because I love history, I just learned this recently in a colloquium by Angela Krieger, who gave a colloquium a few weeks ago here on her book called Life Atomic, which is very interesting. And she talked about the early work by John Lawrence, who was a medical doctor and the brother of Ernest Lawrence. And back in those days, the first early days of the cyclotron, they were producing radioisotopes and started thinking how to apply these to medicine. And one of them was already to try and address deficiencies in iron metabolism. At the time, they didn't have high resolution mass spectrometers and they couldn't produce other forms of iron. So what they did is they produced iron 59, which is a radioisotope of iron with a 44.5-day half-life. And they, if you can believe it, they administered it, fed it through a food or beverage supplement, probably in the form of orange juice, to toddlers. And then they took blood samples and literally detected the radioactivity in the blood. This is unthinkable today, but back then, that was the only way they could do it. But today, we have an alternative, and that was what was pioneered by Steve Abrams at first at Baylor College of Medicine, and then now he moved here to UT, where we are working together closely. But the idea is to enrich stable but rare isotopes of iron. Iron 57 is about 2% abundant, and iron 58 is about 0.2%. And by enriching them and then spiking a food or beverage like orange juice, you can conduct large-scale population studies. It's completely safe because no radioactivity is involved. You measure the bioabsorption in blood, but the bottlenecks, why this has not been implemented so far is because of two bottlenecks. One is the cost, rather prohibitive cost and availability of these rare isotopes of iron. To give you an idea, 1 milligram of iron 58 costs about $100, $100,000 per gram. So that's prohibitive. Secondly, one needs to use prohibitively expensive mass spectrometers where because you have to purify it to avoid mass interferences, because you're only detecting charge to mass ratio, you can only process about 10 samples a day. You got a multi-million-dollar machine that's being tied up with 10 samples a day. So it really can't be applied to large population studies. So we are developing together here at UT and then at the Pointsman Foundation, ultrasensitive laser spectroscopy and simple sample preparation, which will make scalable low testing feasible with small blood samples. And we will produce the stable isotopes at the Pointsman lab. This will ultimately be applied through population studies, through government contracts worldwide to prevent iron deficiency country by country. So the potential impact here is really tremendous. Finally, and I'm almost out of time, so I just wanted to conclude by saying that isotopes are not only important for medicine, but also for basic science. And there are potential discoveries. And I'll just focus, because of short time, I'll just mention two things that I'm involved in, and two preprints that were posted on the archive very recently, and you can look them up yourself. They were also submitted for publication. The first one has a somewhat provocative title called Do Atoms Age? I won't tell you what it's about, so you have to look up the archive paper if you want to find out. But it's an interesting idea. It has never been tested before with radioactive atoms, essentially to run an atomic clock on short-lived or medium-lived isotopes. And we have several candidates that we can produce at the Pointsman lab, such as strontium-85 and strontium-89. The second one was actually, I was very happy to be able to do this. This has some history. This paper was motivated by a paper by my mentor and hero, Steven Weinberg, who sadly passed away this past summer. His paper from 2016 proposed an extension of quantum mechanics that would include coupling to the environment. And he actually predicted something that could be physically measured, that would be a testable prediction. At the time, he had his basic idea was that if you have a clock, an atomic clock transition, there would be a clock shift, but you couldn't see it on a single clock because you wouldn't know what's the environmentally caused shift versus what's the natural clock transition. So instead, what Steve said is if you had an atom where you had 3 connected clock transitions, then you have A to B to C. So you can drive a clock from A to B, B to C, or A to C, and you can call the first one 1 and the second one 2 and the third one 3. Then in quantum mechanics, 1 + 2 = 3. But in Steve's proposed extension to quantum mechanics, 1 + 2 might equal 3 + epsilon. And the question is, could one find this epsilon? If so, if this was found, this would be really a major discovery. Unfortunately, at the time when Steve was working on this, he asked me, and I think he asked David Wineland for suggestions on realistic atoms, and we couldn't come up with any at that time. But revisiting this problem in the fall after Steve passed away, and I discussed this with a colleague, I think both are attending this talk, Dima Butker and Jerry Gilbert. And Jerry, by the way, is another Steven Weinberg student. We came up with a realistic way that we proposed. So with using the ytterbium-171, where this could actually be tested. And we hope that this will stimulate experiments to see if this extension of quantum mechanics is in fact true. So again, here's an example where isotopes could make new discoveries of very basic fundamental physics. So I'm out of time. I will end here. And one more thing I will say, though, before I end, is that the vision for this Pointsman Foundation goes beyond isotopes. And I wrote a commentary in Physics Today, which I encourage you to read. It is entitled, Let's Recreate Bell Labs. And the idea is to make a Pointsman laboratory for creative research. It will be funded and started with the isotopes because of our model, which is kind of a unique model of a for-profit, nonprofit model. We will be able, I believe, to sustain the operations, but we hope to get participation by other foundations to join forces to make this happen. And if so, we could create a place where, similar to Bell Labs, where new discoveries could be made. I think the isotope work and other inventions are really only the starting point. So there's great potential for discovery. So I'll end here. You can look us up on the web, www.pointsman.org. And I thank you for your attention.
Thank you very much, Mark. Very, very nice talk. And so we have